This is Sudeep Bhattacharjee, author of this book, speaking. This is a book I hope will be of some use to some of you. So I'm just going to introduce very briefly the contents of this book on finite element analysis of solids and structures. Well, everything is known about FEA. So why do you need another book? There are many good books with many different concepts, and here I am just showing few of these very good books that exist. And obviously there are also many different software products for doing many different tasks, starting from design to the modeling to the analysis, etc. So question is, why do I need another book on finite element analysis of solids and structures? This book is a synthesis of my teaching work at different universities over the past many years, plus my civil and automotive industrial work experience that have taught me what is important for real engineering applications. So this book is not only just representing my academic work experience or my teaching and research, but also my many years of working in the industry and finding out what is really important that I should know for doing my work. And if you are an engineer like me, hopefully you will find some valuable tips and information in this book. What do I have in this book? There are 12 discrete chapters, theme-based chapters, and each chapter is focusing on one particular item. But again, you can also break down this book in some bigger themes or topics. Matrix method of structural analysis is introduced first. Theory of elasticity is a very important component in finite element formulation. So that is covered not only in chapter 2, but also it is spread through multiple chapters later on. Chapters 3, 5, 6, and 7 basically describe the finite element formulations of different types for analysis applications. Chapters 4, 8, and 9 focus on CAE applications, how to use this technique for computer-aided engineering analysis and engineering conclusions. 10 and 11 focus specifically on dynamics of structures, and the final chapter is on nonlinearity or nonlinear analysis of structures. So let's go through them very briefly so you will get some idea of what to see there. Book starts with a very basic definition. What is stiffness? And you will get thorough discussion in the book, but at least it is showing you where it starts from for very basic simple definition, and it also uses the easy to understand engineering language or notation to describe the concepts. And what I mean by it is basically matrices and vectors that I'm using to describe the parameters and the variables in an analysis model. And that should be pretty easily understood by the students and the engineers, because you can explicitly see what is what in pictures, in equations, and all the steps that are described in the book. So matrix method of structural analysis is basically, you can say, the solution of the equilibrium of a system, static or dynamic, by using matrices and vectors. How does finite element come into this picture? Or what is really finite element in a nutshell, just to introduce the idea. So if you have a body subjected to some external forces and constraints on motion, you can imagine a solid body to be an assembly of finite size elements of standard geometric shape. Standard geometric shape, small elements that we can understand, we can do some calculations for, and assume a general bigger body to be an assembly of such elements. That's the, you can say, basic idea of finite element method. System equilibrium is expressed in these matrix methods of equilibrium system equations, and then you basically solve the equation. So finite element solution is an extension of the matrix method of structural analysis. You figure out the stiffness of the whole system, and then you calculate the displacements at the different, what we call the nodes or degrees of freedom. And this system on the left side represents the internal resistance of the system must be in equilibrium with the externally applied force vector. And this system equilibrium equation can be derived by using the principle of virtual work, minimization of the potential energy, such you can say theoretical structural mechanics concept. But at the end, everything boils down to these equilibrium equations in matrix form. So theory of elasticity, how does it play a role in these finite element simulations or finite element methods? It starts again the book from very basic concept. What is strain? And you are going to get graphical as well as some text description of what strain is and how it is measured in a body. Similarly, what is stress? And you're going to see pretty good descriptions starting from very elementary description to, you can say, the standard definition of the stress components in the body. Now, what is Hooke's law? If you have the stresses in the body and you have the strains or deformation in the body, how are those related? And that relationship is defined by Hooke's law. So it's a very, very important relationship that is utilized in finite element formulations for solving a structural response problem. So finite element formulations vary depending on what you are assuming for the behavior of the body or the part or the structure. So those highlighted chapters 3, 5, 6, and 7, they focus on the finite element formulations in good details. So you will get the basic understanding of the mechanics of formulations, as well as, or the most important, is the behavior of each element that will help you to guide when to use which element for doing some structural simulations. So obviously it starts from theory of elasticity for any element formulation, defining the stress-strain relationship. And finite element formulation basically defines the relationship between strains with the displacement function in a body. Say here, I am showing here linear variation of displacement going from one point to the other point within the element. And we are going to find the relationship of strain within the body to the nodal degrees of freedom or deformations with some derivatives there. Once these two relationships are defined, stress-strain relationships and strain displacement relationship, so stiffness of the element is calculated through some numerical intrications. Again, the derivation of it, why is it like this, is there already in the book, but I'm just showing you the highlight of how things are explained in the book. Now, important thing here to realize is that the behavior of the element depends on what assumptions we made. If I made linear variation assumption for the displacement, so that's what the element is going to produce, and that's what your stresses and strains are going to be related to. So that physical behavior of the element and how it is represented in the formulation is a very, very critical element to understand, so we can successfully use finite elements to predict some response of a more complex system. So I explained that idea here with a two-dimensional graphics of an element. Similar explanations are there for three-dimensional solids. And each step of the way, I also bring in the example of how to describe such concepts or such, you can say, analysis steps in a computer-aided analysis scheme. If you're using, for example, Abacus software for doing the analysis, how do you describe that finite element concept? And here, for example, if I have this 8-node solid element, this is how it is described. And the book does explain all these things in a step-by-step way. So elements used in FEM model really affect the quality of results. So it is very important to understand the behavior of an element and the formulation that goes with it, so that we can knowledgeably use that technique for solving our problems. So book's focus is not on matrix analysis itself and practicing the matrix solution. The book's focus is more on explaining the behavior of the elements, the formulations that go with the elements, and how to use it in different problem solutions. Beam element is another example, and this is also there explained in the book. Shell element is another widely used formulation in structural analysis. And if you're talking about a relatively thicker shell, not too thin, then the resistance mechanisms of the shell are described by membrane resistance, the bending resistance, and obviously resistance to shear deformation. And for each of these mechanisms, the formulation for stiffness is just shown here. Well, I just very briefly explain the element formulations. The book does describe few more details in the book for understanding, and obviously I give references to many other good textbooks that exist in the public domain that you can go to understand even more, plus the software manuals. Each software comes with a theoretical manual where all the element behavior formulations, etc., are documented. So those are also very good sources for learning. My book is to basically explain the physical behavior of few standard elements that can be used for solving commonly available structural problems. Now, what we call the computer-aided engineering or CAE applications need few more things than just element formulations and matrix methods of analysis. So those ideas are explained in those chapters 4, 8, and 9. So what is the role of an engineer in this computer-aided analysis of structures? Engineer needs to define a problem. What is that problem? What loads and boundary conditions are acting on the body, and what is the shape of the body, and how to imagine or visualize the behavior of the body under those external loads and boundary conditions. So that's what I mean, that define the problem, understanding the problem and visualizing the behavior of it so we can build a model correctly for analyzing it. So analyst prepares the finite element model based on the understanding of how the structure or the component is behaving. That's the role or the responsibility of the engineer. So those blue boxes are highlighting where the engineer makes the decision and then gives the input to the computer. Once the model is described, basically a model data file or input file is prepared, and that is sent to a black box software like Abacus for doing the analysis, which will give you a series of results. What I say the black box, because the black box does the analysis that we don't see, but it does follow all those principles that are explained in finite element formulations, in matrix methods of structural analysis, etc. But those things are happening behind our view. And that's why I call it is a black box. But it is important to understand those basic principles of finite element formulations so we can visualize the problem behavior and define the problem correctly, and we can build the correct model for it. Once we understand those two things, we can choose the correct formulations from a software and send the model to it to get the good results that we can use. Next step, an engineer's responsibility is also to interpret the results. A software can also crunch the numbers and give the numbers, but it is the engineer's responsibility to visualize the problem, then to model it correctly, send it to the solver, which gives us the result files, and then engineer has to again interpret those results and make engineering decisions. So those blue boxes are the ones where I give some emphasis in the book. One important thing to know for building the successful model is to understand how a data file is built for a FEA solver. It is important so that when something goes wrong in the model preparations, it can be debugged very easily. So you can use a text editor to see how this data structure has been built. And it is explained with a very simple, say, 2 cable element example here. So you have some node descriptions, a coordinate system described. So you define all your nodes with its coordinates. You identify the elements in a model. Elements are defined in the data file. And you have to choose what element type are you using. That's where the engineering intuition plays a critical role. I have to understand how this member is going to behave, and accordingly I'm going to choose a particular type of element for modeling the structure. Properties of the elements like cross-sectional area, material properties, for example, Young's modulus, Poisson's ratio, etc. Could be more complex descriptions depending on the problem that you're analyzing, but that's the simplest problem that we are describing here. Boundary conditions on the structure, and then asking Abacus to do some analysis. Here we are just applying some static loads at a particular location, and we are asking for some result output. That's the basic description of any data file for any FEA software. Only thing, the rules are, or the syntax rules are a bit different on how to write those things. But basically, all the finite element data structure look, I would say, pretty similar. They all need to know the nodes and elements and element properties and material properties and boundary conditions and load descriptions and analysis type that you want to do. Those basic inputs need to be there in every FEA package for every analysis you want to do. Only difference from software to software is how these things are written, or the language is slightly different. So you have to follow a different rule for a different software. And obviously some software products have little more capabilities, some have little less capabilities. So those things you can learn as you use more and more products. Okay, so in the software landscape, you have many different tools specialized for many different use. Here is a partial list of some of the CA tools that you can use for design and analysis of structures. First part, which I just kept here in gray font, basically the design tools, where you basically develop the graphics design of a component or a structure. But my book is not focused on that part. We assume that you know it or somebody knows it very well and delivers a CAD computer-aided design, a geometric description of a component or a structure. Next step for analysis is to basically build a model, which is what I explained earlier with a two-element cable model, but it could be more complex model. That model can be built based on the CAD design that is available, or some of the software that are for modeling, they can also allow you to build some CAD model or graphics model within those tools. But the specialization of those tools like ANSA or HyperMesh, they're really very good and powerful for building a complex model from a complex CAD data, no matter where the CAD data is coming from. If it comes in a standard format, you can import it into any of these files, any of these software products, and you can build a model for it. When you are building a model, you need to know what software you're going to do the analysis with. And here is the list, like Abacus, ANSYS, Nastran, LSN, etc., etc. There are many products available in the market. And not all are same. And they have different specialization for different types of problem solutions. This book, I focused basically using the HyperMesh for building a model for Abacus analysis and using the Abacus for doing the number crunching for static problems and dynamic problems. So that's how I laid out the book. So at least you get one set of tools that you can use for model building and the analysis, and eventually you can also visualize or post-process the results by using another set of tools. Now, why I am showing this piece by pieces? You can also do some model building, analysis, and visualization in one of these software graphics interfaces like ANSYS. You can do all that within the ANSYS framework. But then you are limited to ANSYS only. If you want to have a very general way of building the model for multiple solvers, then it's better to learn a general purpose pre-processing tool. And then you can send the model to one of the software products depending on what analysis you want to do, and once the result is out, you take it to another general post processor and then you look at the results. I think this is the best way of learning many different tools, and use the tools based on their efficiencies and specialties in particular task. All right. For example, hypermesh, you can bring a CAD model here and then build an finite element mesh in it. And you can check the quality of the mesh, how good or bad that thing is. And if the quality metric is not looking good, you may have to go and remesh the whole thing. So model preparation and quality checks with hypermesh, that's what I'm showing here as an example. The book in chapter 4 gives you A to G process steps descriptions of how to go about all this stuff. You basically start with process A, step A, B, C, D, E, F, and G. The final step, once the model is built correctly, quality check is done, and then you export it for a solver analysis. Engineer is in control at every step of the process. And this is where the skill of the engineer is very important, depending on what you want to do. What you expect from that model will dictate what choices you make every step of the way. For more details, you can even see a video file that is included with the book. Here is just an example. A problem is given. How does an engineer decide what to do? And this is a critical step an engineer will have to take. What element type to use or choose to build a model? Model details will depend on the analysis objective. What am I trying to get out of that model? And that dictates how I'm going to build the model. If I am looking for a very quick deflection analysis for a system like this, I can build a simple beam model and do a load deflection analysis. If I am looking for a little more advanced information, for example, if I want to know how is this upper flange of this thin wall structure deflecting or even flexing under an externally applied load, then it is better to represent this component or structure with shell elements on its mid surface. Then I can see some local deflections in certain areas. If I am interested to see very detailed stress and strain values at some critical areas and I want to understand the safety and integrity of this component, then probably you can just go and describe the entire geometry with 3D solid elements. So there are many ways of modeling a same component. Or in a big system, you may have components built with many different elements and put together. For example, this is an assembly of an vehicle system, which is basically built from thousands of shell and solid and beam elements to put the entire assembly together. Now, how do you manage the data for such a complex assembly of many different components? That idea is also explained here in the book. It is not part of finite element formulation, but is more like the database management for finite element modeling and analysis. So this book gives you a little more information of how to manage your daily life. Use as many parts as you need to describe a complex system, and use a modular approach to assemble the model. Now, once you have built the model correctly, you send it to the solver, you get your results. So you decided about your material behavior, you decided what kind of elements to use, and based on those understandings and visualization, you built a complete model. You send the model to your analysis software, you got the results. Now the question is what to do with those results. If you're wondering what to do, then chapter 9 could help you in certain areas. Here is just one very small example. You can define your load cases, you can build a model, and you can do some static load deflection analysis. You can use those load deflection analysis knowledge or data with material fatigue life information and decide about the fatigue life of a structure. This is just one example. There are a few more in the book for different applications. So the purpose of the book is to make a good analyst, not necessarily a good finite element programmer. If you're looking to be a good finite element programmer, then this book does not give you enough information. But if you want to be a good engineer like me, you will have some good tips based on what I have learned in my experiences. Most important thing, above all, is to understand the limitations that are built into a finite element model based on the assumptions that are made, assumptions for material behavior, assumptions for load description, assumptions for geometric description of the components, and the formulations that go into the finite element. All these things affect the result. So engineering analysis success depends on the awareness of FEA limitations. It is not just perfect problem described with a perfect model getting the perfect results. If it were so, there will not be any need for a CA engineer. You can just fit the model in a computer and it can crunch and give you the perfect results. But the role of the CA engineer is to understand all these limitations and then get the results, make a decision that is useful, given that there are so many approximations and limitations there in the whole process. So engineer is in control at every step of the way in successful execution of a CA exercise. Next three chapters, 10, 11, 12, these are, you can consider to be advanced analysis methods for solving some more complex problems. So 10 and 11, these are focused on dynamics of structures, as the titles are showing, the vibration frequency and basically linear dynamic response of structures. You are going to again see the description starting from very basic definitions and principles. What is really vibration? What properties really define the vibration property of a structure? So you will not need a second or third reference, at least to get the background information for each of the problem that you are facing. Obviously, the book gives you references to many other real good books that exist, but this book, you can say, a little guide to solve the standard problems, and for more complex specialized problems, you will have to consult with more complex books that exist already in the world. And as I already mentioned, whenever this book is explaining a concept or a method, side by side, the descriptions are also given how to frame or model that idea in abacus language. For example, if you're going to do vibration frequency analysis, this is how you ask abacus to do the vibration frequency analysis. So these descriptions or the command languages that they are embedded into the text, plus also some examples given in the book, then how to solve it, and once you solve, how to interpret the results. So those things are there. Even getting into more complex concepts like dynamic response analysis of a structure in step-by-step method, there are many different choices, and how do you navigate through those choices and choose what is a good one and a right one? You can have some indications from that book. Like you know about dynamic equilibrium of a system is explained by all these force components against an applied force in time. Implicit time integration means you are going to solve the equilibrium of the entire system in matrices and vectors. And the book has detailed description of it. But if you're looking for other alternatives, for example, instead of implicit, you want to do explicit method. That's also a very popular and powerful method that exists in the book. Obviously, there are many other good books that explain all these details, but this book gives you some graphical as well as very simple description of what are the differences between the methods and when one is more appropriate than the other one. Hopefully, the book helps you to understand some of those things. Final chapter of the book is on nonlinear analysis of structures. There are books, dedicated books on finite element analysis for nonlinear problems alone. So you can have one whole book or multiple books to cover this topic. Here I cover the very basic but useful ideas in one chapter. And this is added for the completeness of the book, so that it starts from very basic metrics method of analysis, going to the theory of elasticity, and then building up the finite element formulations one by one, solving the linear stress strain problems, then the vibration problems, linear dynamic problem. Now non-linearity, I added it in so that you get the basic idea of how to handle it. And here again is just explained with an say Abacus example input file. If you are dealing with nonlinear material behavior, like stress to strain relationship is not just linear elastic, it is beyond elasticity as the deformation becomes higher. How do you describe these things in Abacus? Here is the description. If you anticipate that under load application, the structure will have large displacement with large geometric change happening in the structure, you will need to do nonlinear analysis, including the geometric change during the analysis. So if you are in Abacus, this is how you describe. And the book gives you more information on how the formulation is developed to solve such problems. Another type of nonlinearity that often happens in large deformation structural problems is that the part-to-part distance or part-to-part interactions or contact condition changes with time or with deformation. So how do you describe that? It's a changing condition in your analysis. So if you have a part, you can describe that this is the mustard surface, and then the other parts, surrounding parts, you can describe them as slate parts. And then in between these two parts, when they come too close to each other, you can implement certain resistance so they don't penetrate to each other. Or even if one part is collapsing onto itself, you can introduce some stiffness between the nodes and the element surfaces so that there is no within part intrusion or penetration to maintain the physical compatibility during the deformation phase. So contact changes does introduce a high degree of nonlinearity in analysis, and the book has, I would say, decent descriptions on these mechanisms, plus how to model those things in Abacus. Here is an example of a practice problem, which is, you can say, involving all these complex steps of material nonlinearity, geometric nonlinearity, contact problems, and step-by-step dynamic load and boundary conditions. So this is basically a nonlinear dynamic response analysis where a thin wall box type structure is crushing onto a rigid wall. So chapter and practice problems are very important to achieve the learning objectives. Each chapter offers those practice problems so that can help mature the learning of the materials that have been described in the chapters. With that, here we come to the end of this video. If you are interested about this book, you can get to the publisher's link. You can also check it out in the Amazon site. And thank you very much for watching this video.